and welcome to lecture 3 of module 5 where we are looking at regression and interpolation. In the previous two modules we introduced what we meant by regression, what we meant by interpolation, and then we looked at various different ways of linear interpolation. Started off with fitting a straight line y equal to a0 plus a1x, and then extended that to multilinear regression where y in general will be a function of more than one variables. The example that we took was a0 plus a1x plus a2u plus a3w, and we saw that the overall equations that we get follow a certain pattern, and we can reduce the problem of finding a0, a1, a2 and a3 and so on to the problem of solving n linear equations in n unknowns. That was the first method that we looked at. The second method that we considered after that was a matrix based method where we wrote our equation as y equal to the linear function plus error, and then it amounted to a least squares problem. What we are going to do today is look at polynomial fit and fitting of some functional forms which are essentially non-linear functions, but which we can linearize them and then go ahead and use linear or multilinear regression in the same form. Okay, so starting off with the polynomial fitting, an example of this would be the specific heat Cp is written as a function of temperature, and it might be a polynomial function of temperature, and we can write this as a0 plus a1t plus a2t squared plus a3t to the power 3. Okay, so this is a polynomial fit that we want to obtain. We want to obtain a0, a1, a2 and a3 such that the error between the Cp computed by the model using this value and the error between and the Cp value that is obtained from the data is minimized. So in this case the data that we have is going to be Cp1, or rather I should write T1 Cp1, because we have been writing it in the form x comma y, where x is the independent variable and y is the dependent variable. So we have T1 Cp1, T2 Cp2 and so on up to Tn Cpn. Okay, so this is the data that we have. So let us now define yi as nothing but Cpi, xi is going to be nothing but Ti, ui is nothing but Ti squared, and wi is nothing but Ti cubed. Okay, so with this definition, yi as Cpi, xi as Ti, ui as Ti squared and wi as Ti cubed, what we can say is that the overall equation that we now want to fit okay, so it amounts to now fitting the functional form a0 plus a1x plus a2u plus a3w. In this case x1, x2 and x, u and w are not three independent variables as we had in the previous lecture, but instead x is going to be temperature T, u is T squared and w is T cubed. Okay. Once we write it in this form, we can then use the same ideas of multilinear regression, and we can then go ahead and obtain the overall solution, and this is going to work as well as a general multilinear regression of that form as well. So let us see what we got in the multilinear regression case for this particular model. For this model, what we had is the matrix Y was defined as y1, y2 and so on up to yn. Y, recall, is nothing but Cp, so we have Cp1, Cp2 and so on up to Cpn. That is going to be our vector Y. Our matrix X, if you recall from the previous lecture, the first column of matrix X was 1 1 1 1 repeated n times. The second column was x1, x2, x3 up to xn, third column u1, u2, u3 up to un, and fourth column w1, w2, w3 up to wn. Using the relationship that we have just written a few moments back, we can write x as 1 1 and so on up to 1. We have n number of ones over here. Next is going to be t1, t2 and so on up to tn, t1 squared, t2 squared and so on up to tn squared, and t1 cubed, t2 cubed and so on up to tn cubed. Okay. So this is going to be our y, this is going to be our x, and our a0, a1, a2 and a3 are going to be nothing but x transpose x inverse multiplied by x transpose multiplied by y. This particular term x transpose x inverse x transpose is known as the left inverse of matrix X. Okay. So this is what is the functional form. This is how we go ahead and do the polynomial regression. For in general, we have n data points and we want to fit an mth order polynomial. So to extend it from this particular case to a general mth order polynomial, if we need to extend it, all we need is additional columns in this particular matrix. So if extending it to n to mth order polynomial, in that case, so I will erase this particular column also. So we will have t1 squared, t2 squared up to t2 to the power n, t1 cubed, t2 cubed up to t2 to the power tn to the power 2 and so on up to t1 to the power m, t2 to the power m and so on up to tn to the power m. And this is what we will get if we have to extend it to a general mth order polynomial in temperature. What the first thing that is necessary in a case like this is that m has to definitely be less than n. You cannot have m to be equal to or greater than n. In general, m has to be much lesser than n for this to work. If we do not have that particular condition satisfied, this particular left inverse of the matrix will not exist, and if the left inverse does not exist, there will not be a least square solution a0, a1, a2 up to am plus 1. Keep in mind that the number of coefficients that we are going to find through this procedure are going to be one more than the order of this equation. Why? Because we have the first coefficient as a0, so we will have a0, a1 up to am, that makes total of m plus 1 coefficients that we need to obtain through this least squares procedure. Okay, so this is what is known as the polynomial regression. A few words of caution for polynomial regression. First thing is the polynomial fit that you want to obtain. If you have the number of data points as capital N, the order m has to be in general much less than the value of n in order for you to have a good confidence on the values of the coefficients that you have obtained. Of course, if the values of the if m is of the order of n or m is 1 less than n, in that particular case what we will end up having is overfitting of the polynomial. So if okay, polynomial will be overfit, which basically means that you can perhaps use this as one way of doing interpolation, but in order to get a regression fit, this is a very poor way of getting a regression fit. In general, to fit an mth order polynomial, my rule of thumb that I use essentially is n should be about 2 or 3 times, at least 2 or 3 times greater than the value of m. The second problem is, as m increases, the matrix X becomes ill conditioned. Okay. What we mean by the matrix becoming ill conditioned is that the inverse of the matrix, there is going to be lot of errors, there is possibly going to be a lot of errors associated with the inverse of the matrix. In other words, what ill conditioning really means is that the largest eigenvalue of the matrix X transpose X is several orders of magnitude greater than the smallest eigenvalue of X transpose X. When we are inverting a number, for example, if we were to invert a number say 1000, when we invert it, that number becomes 0.001. On the other hand, if we are inverting a number say 10 to the power minus 5, when we invert that, the inverse becomes 10 to the power 5. As a result, the small numbers in X transpose, in some ways, again I am using pedagogical liberties over here, but the small numbers in X transpose X, or the small eigenvalues in X transpose X, become large eigenvalues in its inverse. As a result, small errors in those eigenvalues appear as very large errors when you try to invert the matrix. Because of this, when we try to invert a particular matrix, we have to ensure essentially that the largest eigenvalue divided by the smallest eigenvalue should not be a very large number. Usually what will happen, if let us say if m becomes greater than or equal to, and again I am using an approximately equal to sign, say m becomes greater than or equal to 6, the matrix becomes fairly ill conditioned in that lambda max divided by lambda min starts becoming greater than 10 to the power 10. At under these conditions, if you try to invert the matrix S X transpose X, an inversion algorithm that we are trying to use should give a warning that this particular matrix is going to be ill conditioned, and we may not be able to rely on the results that we obtain from this matrix. Okay. So that is essentially what I wanted to cover about polynomial regression. Next we go on to functional regression. okay. And the idea over here is the same idea that we used while fitting the rate law, the Arrhenius rate law. For example, when we had the rate constant k equal to k0 e to the power minus e by rt, we took logarithm on both sides, and when we took the logarithm, we actually got ln k. I'll just write it again, k equal to k0 e to the power minus e by rt. When we took the logarithm, we will get ln of k is ln k0 plus minus e by r multiplied by minus 1 by t, okay. So in this particular case, our ln k was our y and 1 by t minus 1 by t was our x. So when we plotted essentially ln k against minus 1 by t, we got this particular curve as a straight line with the y intercept as ln k0 and the slope as the activation, the dimensionless activation energy E by r, okay. It's actually not dimensionless activation energy, it's activation energy E by r, okay. So that's what we got when we took logarithm over here. Another example comes from biological systems. Enzymatic kinetics follow what is known as the Michaelis-Menten's kinetics, and over there the rate constant k is going to be, or the rate r is going to be given by some constant k multiplied by the substrate S divided by Km plus S, which is Km is going to be a saturation constant and S is the concentration of the substrate that we are interested in. And when we invert this particular expression, we will get 1 by r is going to be equal to Km plus S divided by K plus S, sorry, divided by Ks, not K plus S, which we can write this down as Km divided by K multiplied by 1 by S plus 1 by K, okay. So in this particular expression, 1 by r is our y, 1 by S is going to be our x. This particular term that we have, Km divided by K, is going to be our A1 and 1 by K is going to be our A0, okay. So when we try to do a linear regression or try to fit a straight line between 1 divided by r as the y axis and 1 divided by S as the x axis, 1 by rate constant k is going to be our intercept, the y intercept, and the slope is going to be nothing but the saturation constant Km divided by the rate constant k, okay. So that would be another example of functional regression of any particular functional form. Third example that we can look at is a power law type of a model. Let us say we have a model which of the form mu equal to k times x to the power alpha. We can then again take logarithm of that, okay, and then we will have ln of mu is going to be equal to ln of k plus alpha times ln of x, okay. So ln of mu becomes our y, our ln of x becomes our nu x, our alpha is the slope A1 and ln k is the intercept A0, okay. So this is what we get. So there are a lot of functions of interest to chemical engineers, especially they arise in rate expressions of various different forms, and under those conditions we can actually do some straightforward manipulation of those equations in order to get those equations in a functional form which would still be linear in a modified parameter, whereas it can be non-linear in x. Okay, x is the independent variable, and that is essentially a very important point when we talk about linear regression. For example, all these functional forms, if we look at, they are reduced to y equal to a0 plus a1x, y equal to a0 plus a1x, y equal to a0 plus a1x. X as such is a non-linear function of the independent variable, y itself could be a non-linear function of the dependent variable, but in either case, whether they are non-linear functions or not, finally the functional form that we are going to use in order to do the fitting should be a linear functional form of the type y equal to a0 plus a1x plus a2u plus a3w and so on and so forth. If we go on back to what we looked at when we talked about the polynomial fitting part, so this is what we did with our polynomial fitting, and one of the questions that often get asked, but this is not a linear equation, so how can we do a linear fit? Well, it is not linear in terms of the temperature T. However, in terms of the parameters a0, a1, a2 and a3, this is indeed linear. What does linearity essentially mean? Linearity basically means that there is either a multiplication of that particular parameter by a scalar quantity or a known constant quantity, or there is just simple addition. There are no sine terms, no exponential terms, no power terms and so on and so forth in the quantity that we are interested in. And when we talk about regression or curve fitting, the quantity that we are interested in regression is the parameters okay. So these are the parameters that we are interested in. So our overall expression has to be linear in parameter space. So if we look at the parameters a0, a1, a2, a3, there is no term a0 squared or a1 squared or a2 squared or something to the power a0, a1, a2, so on and so forth. As a result of this polynomial fitting that we have is still a linear fitting. However, there are certain other conditions where the fitting may not necessarily be linear, and the cases where, for example, the fittings are non-linear, of course, the obvious example where the fitting is non-linear is indeed if we write k0 as k e to the power minus e by rt, and we are interested in finding out e and k equal to k0 e to the power minus e by rt, and we are interested in finding out k0 and e without wanting to go through the transformation by taking a logarithm. If we do not do that transformation, indeed this is a non-linear example. It is only after the logarithm transformation that we will get this particular equation as, say, a linear equation. Okay. The other example, so likewise the other example was a saturation type type of an example where we saw R equal to Ks divided by K plus S. In this particular equation, again we had this as a linear form, which it can be converted into a linear form essentially by doing certain transformations. However, instead of this, if we, let's say for argument's sake, we had this particular equation as say e to the power minus e by RT. Okay, in a case like this, it's going to be difficult, or in this particular case, it's not going to be possible for us to perhaps split this into a functional form which is going to be linear in the various parameter space. Sometimes it's not possible to do that, and when that is not possible, then we will need, if we want to fit we want to do a non-linear parameter fitting, then we need to go to non-linear regression, or non-linear regression is non-linear parameter fitting. Okay, so non-linear parameter fitting will be used when the model that we have developed is going to be non-linear in the parameter space. It may be linear or non-linear in the input output space, but it has to be non-linear. It cannot be linear in parameter space. If it is linear in parameter space, of course we will go ahead and use the linear fitting in this particular case. Okay, and we will look at the Gauss-Newton method for non-linear regression in a short while. So let's say we have the data x1 y1, x2 y2, and so on up to xn yn. Okay, what we have seen so far is we tried to fit a functional form, a linear form of the form y equal to a0 plus a1x. The other possibility is to fit the form x equal to b0 plus b1y. Okay. The question that one would ask is, this particular form and this particular form, since both are linear, they ought to be equivalent. So the question is whether a linear regression technique of this form is going to give us the same straight line or not. For example, let us just rearrange this by subtracting by b0 and dividing by b1. So we will get x minus b0 divided by b1 equal to y, and comparing it y equal to a0 plus a1x, what we get is a0 is nothing but minus b0 by by b1. I will just write this as plus minus b0 by b1, that is nothing but our a0, and 1 by b1 equal to a1. Okay. So the what I am saying is this, is let us say we have data as before, okay, and let us say we got this particular curve as y equal to a0 plus a1x. When we try to fit another linear form x equal to b0 plus b1y, what we see over here is with a straightforward division of this type, b0 by b1 multiplied by minus 1 and 1 by b1, we will get this to be converted into y equal to a0 plus a1x. Now the question is the curve y equal to a0 plus a1x obtained from this particular method, and the lines, not the curve, the lines, I am sorry, obtained from this particular method, are they going to be one and the same line or not? And the answer to that question is it depends on what we used as our functional form in order to get this this particular regression fit. Remember the functional form that we used in order to get, so this was the model, and then we had certain errors. The errors in this particular case, we assumed yi was a0 plus a1 xi plus ei. In this particular case it's going to be xi equal to b0 plus b1 yi plus ei. So in this case what we are assuming was that the errors are in x, and in this case we are assuming that the errors were in y. So what I mean by this is, let us say this is our best fit curve shown over here, okay. Then what we are actually minimizing, as we had seen in in one of the previous lectures in the module, is we are minimizing these vertical distances between this straight line and the data, okay. This is what we are actually minimizing. But if we have to fit the curve x equal to b0 plus b1y, okay, it is not the vertical distances that we are minimizing, but it is indeed the horizontal distances that we are minimizing, okay. So let us say this is going to be the best fit curve, okay, and this is the best fit curve because we are minimizing these horizontal distances. Okay, so these are the horizontal distances that we are trying to minimize. Under certain cases, yes, we would definitely get our a0 equal to minus b0 by b1 and a1 equal to equal to 1 by b1 to be same as a0 and a1 over here, but in general for most cases that is not going to be true. So the question whether you need to use a functional form y equal to a0 plus a1x or whether you use x equal to b0 plus b1y depends on what you know about the overall system. For example, if we go back to this particular example of trying to fit Cp as a polynomial form with respect to temperature, what we get is essentially there are errors in measurement of the specific heat Cp, there are errors in the measurement of temperature, okay. So there are errors both in x and y. In that case, if we minimize the errors in x versus we minimize the errors in y, we are going to get different results, okay. We will look again, we will take up the example that we had worked in the previous lecture and see what results we will get if we are going to do a regression of the form x equal to b0 plus b1y. So this is what we had done in the previous lecture. We were given the data x and y, this was the data that we got, and then we had obtained summation of x, summation y of y, then we computed xy, and summation of xy we computed x squared and this, and then we obtained a0 and a1 using these formulae, okay. This is the a0 and a1 that we had obtained in the previous lecture. I have just made them boldface. Now what we are going to do is just interchange x and y data, because now x is going to be the dependent variable and y is going to be the independent variable, and in as we had done before, our b0 and b1 will have almost the same form. The only difference is wherever we have x, that will be replaced by y, wherever we had y, that will be replaced by x. So we will have this as indeed the numerator is indeed going to be summation of x multiplied by summation of y divide minus n times summation of x multiplied by y. If you replace essentially x with y and y with x, you are going to get the same expression. However, in the denominator what we will have is we will have summation of y the whole squared minus n times summation of y squared, okay. That is going to be different in this case, and b0 is going to be nothing but x average minus b1 multiplied by y average. This is going to be our value b0, okay. So those are the two main differences really that we will have in this particular example. So, I will just drag it upwards so that it is all visible in a single okay, and I will again just okay. So, this is what we get for B1 and B0. So, for B1 and B0 we will really need is xy, we will need our x0 and now we will also need our y squared, because instead of x squared we will be using y squared in this particular expression. So, y squared is going to be nothing but this to the power 2. Okay, I will just increase the font so that it is all visible for us. Okay, so y squared is going to be this value to the power 2 and I am just going to drag it all the way so that all the data is covered and we will get the summation and then we will just save it over here. Y hat, remember, was nothing but our y that is obtained from the model given x, from the model a0 plus a1 x. So, same way now we are going to try to find b1 value. B1 value is nothing but summation of this is not visible again. So, I will just do this very quickly. Yes, and now we are good to go. Okay. So, now we have the expression for B1. B1 expression is summation of x, which is this value, multiplied by summation of y, which is this value, minus n, which is 6 times summation of xy, which is this particular value. Okay. So, A10 is A10 is summation x, B10 is summation y, C10 is summation of xy and 6 is our n, that is our numerator, divided by the denominator, and the denominator in this case is summation of y the whole squared. This is summation of y, B10 is summation y whole squared minus n, which is 6 multiplied by summation of y squared, that is the value we have recently found, and that is what our B1 is, and B0 is nothing but x average, which is, so okay, I will just change the font size here again because it is not visible. Okay. So, this is nothing but x minus B1 times y whole divided by n, summation of x minus minus B1 multiplied by summation of y whole divided by n, which is n was 6. Okay. So, this is going to be our B0 and the above value was our B1. Let us find out what value of A0 and A1 that we get over here. A1 is nothing but 1 by B1, so equal to 1 divided by B1, which is 0.51, which is different from the previous value that we had obtained, and A0 is nothing but negative B0 by B1. So, A0, and I will just increase the font size here again, equal to negative B0 divided by B1. Okay, and this is the value of A0 and A1 that we will get, corresponding to the fitting of instead of x versus y we have now fitted y versus x. So, for the given x data what is going to be given y data, what is going to be x hat. Again as usual we will just increase the font size before continuing. Okay. So, we have x hat over here. Okay. X hat is nothing but x hat equal to b0 plus b1 multiplied by yi. So, x1 hat is nothing but b0 plus b1 multiplied by y. Okay. Remember what we did in the previous lecture, because the terms b0 and b1 are not going to change when we drag the particular equation downwards, that is why we will put dollar signs over there. Dollar signs basically mean that as we drag this particular column, D18 which is our B0 value and D16 which is B1 value remains the same. The only value that is changing as we drag this particular column downwards is going to be the B3 value that is going to change. Okay. So, I will drag this particular line downwards and this is what we get as x hat. So, now let me add that data to our original data. So, we will add this data. This first guy is going to be x hat, the second is going to be again our x hat value, okay, and the y axis is going to be the y values. Okay. Okay. So, these are essentially our green data points. I will select the green data points and do format data series. Okay, and I will just zoom in format axis and I will just zoom into that that particular axis by taking values of x as from going from 0.7 to going to 5. Okay, and likewise the y axis also will zoom in. The reason why I just want to zoom in and show you essentially is to see that the two regression methods are indeed going to give us different results. Okay. So, we have 2.8. Okay. Okay. So, this red curve that I have highlighted now is the curve that we had fitted the data y hat equal to a0 plus a1 times x hat, and this green curve that I have highlighted now is the data that is fitted is x hat equal to b0 plus b1y. Okay. So, as you can see these two lines are indeed different two different lines. Okay. What happens in case of the red line is we have this minimization of these vertical distances between the data point and between the actual line, whereas in case of the green line the minimization is between the horizontal distances over here between the blue datas and the green data points. Okay. So, this is the two different cases or two different ways in how for the same data the linear regression is behaving. One case when the error is in x variable, the another case is when the error is in y variable. We will go back to the board and we will take up the same chart we will look at again, and we will see what else can actually be done, and this goes into what is known as multivariable data regression type of an idea. What we have done so far, now if we want to go into advanced data analysis stuff which we are not going to cover, but just a very quick 2-minute summary of that is what we have covered so far is what is known as ordinary least squares. Okay. So we are in ordinary least squares, what we are doing is we are minimizing the vertical or horizontal distances or horizontal or vertical error between the best fit line and between the data points. Okay. An alternative to this is what is known as total least squares or error in variable methods and so on and so forth. There are various different methods that use the statistical properties of the data that we have in order to get a better fit of the overall curves, and a simplest way of looking at it is rather than minimizing the vertical distances, we can minimize the perpendicular distance of the particular straight line that best fits the data and the data point. So I will just erase this and draw the various points all over again. Okay, and I am just widely spacing these points so that, okay, and let us say this is the best curve line. So what we have seen when we are trying to fit a0 y equal to a0 plus a1 x, what we have done over there is we had minimized the vertical distances that I am showing as thin white lines. Okay, and when we fitted x equal to b0 plus b1 y, we minimize the horizontal distances. Another alternative is if there are errors in both x and y variables, what we may want to do is to minimize the perpendicular distance of that data point from the line that we have drawn over there. Okay, and some of the advanced techniques allow you to actually do this kinds of least squares minimization. So that essentially covers the linear regression part. In the final few minutes of this particular lecture, I will just talk about non-linear regression. Okay, and let us say that we want to do a non-linear regression when the equation is of the form, say, y equal to some function f of x comma a0 comma a1. Okay, in this particular case, what we will do is we will use a similar idea that we used earlier, for example in Newton-Raphson's method or any of the earlier methods. What we will do is we will linearize the equation f with respect to a0 and with respect to a1. So we will start off with initial guess okay. Next we linearize the function f with respect to a0, we linearize the function and with respect to a1. So f of a0 f of x comma a0 comma a1 can be written as f of x a0 1 a1 1 plus partial f by partial a0 computed at a0 1 a1 1 multiplied by delta a0 plus partial f by partial a1 computed at a0 a1 multiplied by delta A1, okay, and we are ignoring any of the higher order terms over here. So y is going to be nothing but equal to this particular value. We will take this value to our left hand side, and what we will get is this is yi minus f of xi comma xi semicolon a01 a11 is going to be equal to dou f by dou a0 computed at a0 a1. We will call that our u1 or ui, sorry, not u1, okay, and this we can call this as say Vi, okay. So Vi is yi minus f of xi a01 a11, ui is nothing but partial f by partial a0 computed at the current value, and wi is again this particular expression, and from this we will essentially be able to get delta a0 delta a1 is nothing but x transpose x inverse x transpose v, where v is v1 v2 up to v capital N, x is u1 u2 up to u capital N, w1 w2 up to w capital N. So our capital X u1 up to un, w1 up to wn, and our capital V is nothing but v1 and so on up to vn, okay. So the overall procedure is to start with initial guesses a0 and a1, then compute delta a0 and delta a1 using this particular linear regression. Based on delta a0 and delta a1, we will get a02 as a01 plus delta a0, a12 is going to be a11 plus delta a1, and so on, and keep repeating until there is no more change in the delta a0 and delta a1 value, okay. So that essentially ends our the third lecture of this module, and with the third lecture of the fifth module we have finished talking about regression. From the next lecture onwards I will talk about interpolation. In regression what we did is we started off with linear regression and one variable, moved on to multilinear regression. We looked at two different methods of doing multilinear regression. Both of those methods are exactly equivalent to each other, only the expressions are slightly different from each other. Next we looked at the regression in for polynomial functional form, polynomial regression. After that we covered functional regression. Then we took up an example where we compared the regression of the form y equal to a0 plus a1x with the regression of the form x equal to b0 plus b1y. Although those equations could theoretically be for equations for the same line, they are interconvertible into each other. We saw that the two different ways of doing these regression. In the first case we minimize the vertical distances when we plot y versus x. In the second case we minimize the horizontal distances when we plot y versus x, and finally very briefly we covered the nonlinear regression part. Nonlinear regression just involves linearizing the overall regression model with respect to the regression coefficients A0 and A1. Okay. So that is essentially what I intended to cover in regression. For the most part it is linear regression, and the reason why we spoke about non-linear regression as well as total least squares idea is to motivate some of you to go ahead and read up these advanced topics if you have more interest in these topics. From the next lecture onwards we will start talking about interpolation, and we will start off with polynomial interpolation. Thank you.